Testing on YouTube. Testing on YouTube. All right, YouTube works. How's it going? QD, NLP Prompter, Julien Blanchon, DSL, and Isaac Perez. To answer your question, Julien, this is going to be on this paper here, The AI Scientist Towards Fully Automated Open-Ended Scientific Discovery. All right, let's make sure it works on X, and then we'll go. Is it live on X? Kinda, maybe. How's it going? Monk Codes, Oma Viva, and Louder Than Thunder X1. Do you know of a research paper for something like the OpenAI Advanced Voice Mode? This is a question from Oma. I've shared this paper before, but the Mirasol Google paper. Yeah, this one, Mirasol 3B. That's one that I like if you're interested in kind of a multimodal agent kind of thing that has memory. I've shared this paper before, but this is a multimodal, right? Video, audio in. This one has text out, but the important part here is this idea of a kind of external memory, kind of like a I call it like an LSTM or an RNN, right? Where you have this kind of hidden state, but it's not like an actual hidden state. It's an actual memory cache. So it's something in between like RNNs and RAG. But I think that's a good paper if you're interested. How's it going, Steve? Question from Steve. Is there a live every Wednesday? No, I used to do 2 lives. I actually used to do more than that. When I first started, I was doing it basically during the weekdays, almost every day. Then I switched to weekends, so Saturdays and Sundays. But now I'm just doing these once a week. So I try to make it land on Friday, but I had stuff to do, so it's on Wednesday today. All right, guys. I think it's live on X, so we're going to get started. Yeah. Okay. Let me sip some water here. I also have a fancy hat for you guys today. This is a Phrygian hat, or a Papa Smurf hat, as I like to call it. Papa Schtroumpf. I'm more interested in the voice synthesis part. All right. All right, guys, welcome to another Hupo stream. We're going to be looking at a recent paper today. The stream is called AI Scientist. As always, you can find the notes for this stream on this GitHub repo here called Hupo Docs. So we're going to be looking at this paper that came out just a couple days ago. This paper is called The AI Scientist Towards Fully Automated Open-Ended Scientific Discovery. Oh, what happened here? All right, I think I accidentally hit something on my keyboard, but this is a pretty awesome paper where they're basically going to be using a kind of agentic workflow of LLMs feeding output to more LLMs and kind of a bunch of hard-coded prompts. And ultimately, this pipeline creates a paper, machine learning paper specifically. So I think given that we review a bunch of papers on this channel, it makes a ton of sense to look at the system that will basically replace everything we do. How's it going? Niraj NLP and Abdul Hakim Bashir. What do I think of the strawberry confusion on X? I fell a little bit for that trap as well myself. I thought that the strawberry man on X was some kind of agent combined with some people working at OpenAI, but unfortunately it looks like it's not the case. It's probably just some random person LARPing, pretending to be an OpenAI insider, so not super hype, unfortunately. How's it going, Ed and Sagar? Yeah, he's a good marketer. It's kind of like, I think I'm understanding his strategy more. This is Sam Altman, and he realizes that you can kind of outsource your marketing, right? That there's so many people that are eager to kind of engage with him and OpenAI just in general, that he realizes that, hey, if I can just kind of like throw out random engagements and comment on this random person's post, like they do all the stuff for me and I don't even have to do it. So it's a bold strategy. All right, let's get into this paper because there's a lot of stuff here to read and think about. So we're going to start off with the abstract here. So this is a comprehensive framework for fully automatic scientific discovery, which means it generates novel research ideas. It then writes the code. It then executes the experiments, then visualizes the results, describes its findings by writing a full scientific paper, and then runs a simulated review process for evaluation. So that is effectively the entire scientific process, at least when it comes to machine learning research, right? And the scientific process is really only possible in this fully automated way because machine learning research only requires that you kind of interface with reality as much as writing code and executing an experiment, right? So any idea in machine learning, ultimately what you're doing is just writing some code and then running some benchmarks, which can be done entirely on a computer, right? So this isn't going to discover any kind of planetary or like it's never going to solve some kind of like bio type of thing, because all of those kind of more hard sciences require that you actually run a real life experiment, which isn't really possible because robots aren't particularly great right now. But for something like machine learning, all you got to do is just run a bunch of code on some GPU. So you don't really need to actually touch anything in the real world to do that. So that's why we can do this entire automated scientific process with LLMs. They're going to be applying it to 3 distinct subfields of machine learning: diffusion modeling, which is primarily used for image generation. So that's what's behind all the kind of image gen technology. Transformer-based language modeling, that's just your language models. I think there are some LLMs that are not transformer-based, but those are almost more like a novelty thing. Like pretty much every LLM is transformer-based, so I don't know why they need to specify that. And learning dynamics, which is, I guess, a more generic description. What we're doing here is we're automating AI research by using AI itself. There's that Schmidhuber reference. You know, Schmidhuber will explode if you don't cite his papers, so good thing they cited his papers there. You also got some pretty badass references here. Jevons 1877. You know, if you start your paper with a reference that's over 100 years old, you get bonus points. Within the field of machine learning itself, research automation has largely been restricted to hyperparameter and architecture search. So what they're referring to here is whenever you run a machine learning experiment, there's going to be a bunch of these hyperparameters, which is basically numbers such as maybe the width of a neural network, how many layers deep it is, the number of your multi-head attention, how many heads are you using, right? There's all these little tiny numbers that are buried within your architecture that you have to basically pick somewhat arbitrarily. And rather than picking arbitrarily a specific number, what people will pick is a range of numbers, and then they'll have to basically sweep over these different ranges of numbers and all the different permutations of those ranges of numbers and run 100 experiments and then see which specific permutation of these hyperparameters work better, right? And there's a similar kind of idea there with the architecture search, except the search space is a little bit more discretized versus hyperparameter. You can have continuous search spaces. But that has been automated for a long time now, right? That's just part of being a machine learning researcher, is doing these kind of hyperparameter sweeps and neural architecture searches. But these, as I was saying, are within our handcrafted search space. So you as the researcher are kind of picking, okay, these are the 4 different values for the number of heads that I want to try, right? So it's some handcrafted search space. The space in which you search has been designed and picked by a human. Approaches that remain constrained by rigorously defined search spaces and objectives which limit the breadth and depth of possible discoveries, right? You probably will have to venture outside of whatever search space you're constrained to in order to find something new that somebody else hasn't found before. So this AI scientist is given a broad research direction with a simple initial code base, which is a little bit unfortunate. You know, they say here it writes the code, but it really doesn't write the code. All it's really doing is it's kind of modifying an existing code base. So there's a couple letdowns in this paper. That's kind of one of them right there, right? They make it sound a little bit better than it actually is. Really, all it's doing is it's just kind of modifying some existing code base that you give it. So you're kind of already constraining the search space, except now you're going a little bit beyond kind of a handcrafted hyperparameter search space to a search space that includes kind of similar code bases. So you're kind of branching the code a little bit, but I feel like it's still a little bit more constrained than they would like to admit. This approach can be more generally applied to almost any other discipline, biology or physics, given an adequate way of automatically executing experiments. And that's the hard part that I was referencing in the abstract here, is that for something like biology or physics, you're going to actually have to perform experiments in the real world, and we don't really have the tools to do that yet, although I think we're very close, right? I think that there's probably already kind of this robotic process automation for certain types of biology research, right? Where you have like hundreds of test tubes and you have a robot that's basically combining all the different things in all the different test tubes. So there is some form of that, but it's definitely not, I would say it's more similar to hyperparameter search than it is to kind of open-ended science. Schmidt-Huber, great guy. How easy will this framework be to adapt to the social science and humanities? I feel like social sciences and humanities might actually be something that is actually easier to explore, because social sciences and humanities are, the search space for that is almost the search space of text, right? So like anything that is purely text-based, I feel like automated AI research is going to be able to explore that much faster than something that's kind of like hard science, you know, where you actually have to do something in the real world. So maybe we're going to make a ton of progress in the humanities. Okay. By leveraging modern LLM frameworks like chain of thought and self-reflection to improve decision-making. So there's been a bunch of tricks that people have come up with since we saw LLMs pop up several years ago, right? And there's been a bunch of different good ideas that people just basically tack on now. Some of these are chain of thought, right, where you allow the LLM to kind of have a little bit of context where it can kind of think to itself, right? You can output tokens which aren't necessarily the actual token that you want, but more so just prepare and add extra tokens to the context such that the actual tokens that you want have a little bit better context. So you allow the LLM to produce its own chain of thought, which is where it comes from. Self-reflection, which is a very similar concept, but basically allow the LLM to look at its own output and then use that to either judge the output and pick the best outputs. But these ideas are here to stay, chain of thought and self-reflection, and then obviously they form part of this paper. So here in figure 1, we have the workflow, right? There's a new law LLM that has been released, Soul LM, if this could be helpful in your question. Okay, so people have been releasing specific LLMs for law, I suppose. I mean, probably makes sense. The LLM idea plan and innovation. So here you're using the language model to effectively generate the ideas. And this is interesting because this is something that we couldn't really ever do before, but this new wave of AI, right, the generative AI, it is capable of creativity. So that's really why this entire process is possible, is because the LLM can basically find permutations and combinations of ideas that haven't been done before, right? It has creative ability, which is something that we only thought humans were capable of doing, but now machines can do it. And so this is really a core part of it. Novelty check with Semantic Scholar. Semantic Scholar is kind of like a database that has a bunch of existing papers. So creates a bunch of ideas, then it goes and it checks to see which ideas have been done, which ideas have not been done. That's this idea of novelty. Novelty is just a fancy way of saying new. Novelty is like newness, right? So you don't want to test out an idea that somebody's already tested out. Idea scoring and archiving, right? So this is kind of this idea of reflection where it's like looking at the ideas, looking at similar ideas, and then using that to pick, so search through the generation. And this idea of generating a lot of volume with a Gen AI system and then filtering that volume, this is behind the alpha geometry as well. There's a bunch of other LLM papers where they do this. All right, now you get to the experiment iteration. This is where you're going to take your experiment template, which is the code base that you start from. You're going to have a code delta, right, which is basically a modification to the experiment template, and then you're going to run that. And you're going to run that, update the plan, run that, update the plan over and over and over again, right? Which is kind of what you're doing when you're doing machine learning research as a human, right? You're basically taking some existing code base, which is maybe coming from an older student in your lab, and then you're making some modification and then trying it out, right? So even in human machine learning research, creating code entirely from scratch is a little bit unusual. Usually what people do is they'll take some existing code base and kind of extend it a little bit. But then once you do that, you make your plots, right? Hopefully those plots agree with the original idea or hypothesis, and then you can just simply write the paper. So there's a bunch of different ideas and core functionalities that are required for this entire workflow to work, right? There's this idea of using Gen AI creatively to basically get a bunch of ideas, using the ability of LLMs to score or kind of determine which outputs are good, which outputs are bad, this idea of filtering. So there's the generation idea, there's the filtering idea. Then there's the ability of LLMs to change code and write code and modify code. That's what this kind of central part here is. And then you have the ability of LLMs to actually write long form content like a paper. Okay. How do we know the idea is not a madman's rambling? You kind of don't. Like that's, you have some review steps here, right? This idea scoring, and then the LLM paper reviewing, and then also here when you run the experiments, you can also kind of check, but it is very difficult to check this kind of stuff, and that's something that we're gonna touch on in this stream, right? That it's at some point, like, how do you even verify that these ideas make any sense? And that's where you need to be able to run experiments in the real world, right? So in biology or physics, you have some hypothesis, you can actually test it in the real world, and if it works, right? The universe is basically your heuristic or your evaluation function. But for something like machine learning, you don't have, like, kind of, you could think of the running a code and writing code, running that code, and looking at the results of that code is in a way kind of like using the universe to check your idea, but it's not quite the same, right? You can kind of delude yourself into thinking that you're discovering something when really you're not. And that's actually one of the problems with this. So while reading this paper, I discovered something which I feel like they overlooked, but we'll get to that later. Okay. Large language models. They're going to be using all of the big LLMs here. So you have references here for the Google DeepMind, Gemini, Llama 3, 3.1, GPT-4 from OpenAI, and Sonnet from Claude. So I do like that they really look at all the different LLMs here. It's not like they just picked one random LLM and then they just went for that. They actually compared all the different LLMs, and they actually have really nice comparison charts here. Let me see if I can show you guys some of that. For example, here, violin plots showing the distribution of scores generated by the AI scientist reviewer for AI-generated papers across 3 domains. So different LLMs and then LLM reviewer scores, right? So how the LLM reviewer score, the reviewer score is basically how good is the final paper, right? And you can see here they made their workflow in a agnostic way, so you can swap out which LLM you're using, and that allows you to almost see which LLM is performing better. And it does seem like, for example, Sonnet and GPT-4o are kind of at the top of the list here, which agrees with other similar things, right? So here I have another paper, Visual Agent Bench Towards Large Multimodal Models as Visual Foundation Agents. This is basically a benchmark paper for vision language models. And in this one, they also swap out the LLM so you can see which LLMs kind of perform better. This is almost like what I'm trying to show here is that the foundation models that are good at writing scientific papers, such as Sonnet and GPT-4o, also seem to be good for use in a vision language model. GPT-4o, Sonnet, right? So like, you kind of see the same stories over again. And then here I have the famous LM Sysbot chatbot arena leaderboard, and you see it's also GPT-4o. You got Gemini in there, you got Sonnet. So it's the same foundation models that are succeeding in all these different categories. So based on that evidence, I feel like GPT-4o is still kind of state of the art for no matter what you want to do. Okay. Let's go automating AI research. We read that. It's about $15 per paper, which comes down to the cost of actually running this workflow. Let's keep going. This is effectively what a language model is, right? A language model is a model of the conditional probability of a new token, right? It's auto-regressively predicting these tokens based on preceding tokens. So given some sequence of tokens, right, up to time step t, you're trying to predict the next token t, given some parameterized model where the model is a bunch of transformer blocks stacked on top of each other, and those transformer blocks have a bunch of parameters. All of those parameters are this theta, all right? And the output of the model is some probability distribution of like, hey, given all the previous tokens, this is the most likely token. All right. A big part of this is going to be this part here, this experiment iteration, right? Where you're going to start from your experiment template, which is some code base that's themed, right? So maybe it's like a simple diffusion code base. And then you're going to need to generate these code diffs, right? Which is basically just little updates to the code, and then actually run them and see if they perform better or worse than they were performing before. So in order to do that, they're going to be using this state-of-the-art open source coding assistant called Aider. I hadn't really heard about this one before, but interestingly, they say it has a remarkable success rate of 18.9% on the SWE-bench. SWE-bench is a software engineer benchmark. It's basically like a collection of real-world GitHub issues where it kind of like mimics software workflows, right? So if you're good at SWE-bench, then you should be good at generating code diffs for a specific idea given a specific code base. But interestingly, we've actually doubled performance on this, right? So recently it came out. This is another startup that kind of, I don't know if they were out for a while, but like I just got made aware of them, but they got a 30% eval score on SWE-bench. So all of the results in this paper are with a coding assistant that only gets about 20% on SWE-bench. So it'd be super interesting to see what happens if you take this paper and now use one of the stronger AI software engineering LLMs for it. So that's pretty cool. It means that there's more juice to squeeze in this process. George, isn't some of it allowing the LLM to hallucinate a bit more than normal? Yeah, part of the idea generation here is the LLM has randomness in it, right? At the end of the day, it's a probability distribution over all possible tokens, and you want it to almost pick weird tokens, right? You don't want to do some kind of greedy decoding where it only picks the most probable next token, because then you're not going to have a ton of novelty in the idea generation. So yeah, you are correct that you want the LLM to kind of hallucinate a little bit. And it's fine, because this filtering step here where you score the ideas, that's where you're actually going to filter out the hallucinations that are bad. But hopefully you get some hallucinations that are actually good, right? And that's kind of what creativity is, right? I feel like this is the way human creativity works as well, right? You've seen a bunch of stuff in your life, and then what you're kind of producing and what you think is creative is really just your subconscious, just kind of like mixing the Legos together and then coming up with some new thing. All right. 3 main phases, again, the idea generation, experiment iteration, and paper write-up. So you start with a code template and a LaTeX folder that contains style files and section headers, along with some simple plotting code. So LaTeX, this is the, it's kind of like a programming language that you use to actually write papers. So whenever you write a paper like this, right, there's a bunch of extra crap that determines like the font and like the spacing and like all this other crap like that. So whenever the LLM here is writing the paper, it's not writing it from scratch, right? It's basically using some template, and all it's doing is just filling in the text. So there's already the template for not only the code, but for the paper itself. And that's a good idea, right? Because specific conferences and specific journals that you submit papers to have different styles and requirements. So I don't think it makes any sense to kind of come up with a new style, right? You kind of want to just freeze the style and just let the LLM just fill in the text. Each run starts with a representative small-scale experiment relevant to the topic area, which is the starting code template. Okay. All steps, Aider sees its history of execution. So the LLM-based coding assistant here is capable of looking at all the kind of chain of thought that led to this particular code. But the problem I have with this is that it doesn't see from before the starting code template. So it only sees its modifications to the starting code template, but like the starting code template is like, you're already refining that, you're limiting that search space to a little box, which is that little code template. So I don't know if I like this idea. I feel like if you're going to be doing genuinely novel machine learning research, you probably want to start from scratch. And I know that we're just not there yet with the capability of these language models yet, but I feel like this starting code template like really is limiting that search space. Okay. Paper write-up. The AI scientist is allowed 20 rounds to pull the Semantic Scholar API, looking for the most relevant sources to compare and contrast the near-completed paper against for the related works section. So this is the Semantic Scholar here, right? It's allowed, I think it also, when it's reviewing the paper and then also when it's looking at the ideas, it has access to this external database of papers that it can check to see if the idea has been done before, which allows it to kind of validate the novelty of the idea and the potential upside in the idea. Okay. Refinement. It can be overly verbose and repetitive. To resolve this, we perform one final round of self-reflection, section by section. So even though LLMs can kind of produce rambling nonsense, some LLMs are more susceptible to this than others. I think at this point, GPT-4o and Claude, like those LLMs have explicit wording in their system prompt to prevent this kind of like overly verbose kind of like style, but you can still run into that issue. So they resolve that by basically going through the paper and trying to summarize it and filter it down. An LLM reviewer agent. The GPT-4o based agent to conduct paper reviews based on NeurIPS. This used to be called NIPS, but NIPS is the word for nipples in English, so they decided to name it NeurIPS. You know, you don't want a conference called Poo Poo, so they came up with some less trolly name. But numerical scores. So whenever you actually write a paper for some kind of conference like NeurIPS, you submit it, And then you have the peer review process, which is a bunch of people that are chosen by this conference, look at a bunch of papers, and the papers are anonymized. So whenever you're reviewing papers, you'll receive something that kind of looks like this. Let me see if I can find it right. It'll say something like anonymous authors, like papers under double-blind review. But this is honestly a bunch of bullshit, because there's a lot of problems with peer review, but one of the bigger problems is that even if you anonymize the authors, the paper itself usually is very obvious in terms of who did the research, right? You can, if they're using TPUs, you probably know it's Google. If they have certain kind of, you kind of know who the paper is from. So even though it's double blind, like a lot of reviewers, they just kind of look at the paper, and if they can kind of recognize that it's a paper coming out of like a big industry research lab, then they just kind of rubber stamp it and it's fine. And then if they look at the paper and they're like, I don't know who this is from, they kind of reject it. So unfortunately, the peer review process isn't great. So in a way, this type of automated LLM reviewing is probably better. But ultimately what the reviewer gives is a score, right? Which is kind of like a cooking competition where it's like you cook some ribs and it's like a 3 out of 5 ribs. Like there's kind of similar arbitrary score here that accounts for soundness, presentation, contribution, overall confidence, list of weakness and strengths, as well as a preliminary binary decision. So you live and die by that accept or reject. I think there's levels to that as well. So there's like strong accept, weak reject, strong reject. But different conferences have their different ways of reviewing. So they took the ground truth data for 500 iClear 2022 papers extracted from the publicly available open review dataset. And then they use this as kind of like a way to determine if their automated reviewer is actually reviewing the papers correctly. So whenever they're evaluating their automated review LLM, they are giving it real papers as well. And those real papers have quote unquote ground truth data, which again, because the peer review process is kind of broken, I would argue that this ground truth data of 500 iClear 2022 papers is probably kind of biased as well. But they do say here that the automated reviewer achieves superhuman F1 scores and human level AUC, area under the curve, which is basically saying, okay, well, we gave it some real papers. Was it able to actually get the score correct, right? This review score for the papers that we know the review score for. And it is capable of doing that. So here you go. Uncalibrated versus calibrated. Sonnet versus GPT-4o. They're kind of about the same, to be honest. All of these are false positive rate, false negative rate. These are all different accuracy type scores, right? So false positive rate, how many times did it say this is an acceptable paper, but it's not an acceptable paper? False negative rate, how many times did it reject the paper when it really should have accepted the paper, right? The false negative rate is much lower than the human baseline. Hence, the LLM-based reviewer agent rejects fewer high-quality papers, but the false positive rate is higher, highlighting the room for potential future improvements. It's, I don't know if I necessarily want to read too much into this, because honestly, 500 iClear papers is just not a very big data set. So any kind of weirdness in these type of scores here is probably just resulting from the fact that this is a very small data set. So I would say if we're capable of expanding this to 10,000 reviews or 1 million reviews, right, then I would expect these automated LLM reviewers to become better and better and better over time as well. Let me see. Aider is awesome. Okay, so we got some Aider fans in the chat. How people think cannot... It'd be nice to hear someone say latex. Yeah, I think the way that like the way you're intended to say it is latex or something like that, but it literally sounds like latex. It looks like latex, so I don't know. You can't publish code on GitHub before the end of the peer review. Yeah, you're really not supposed. So like a lot of these conferences, they basically don't want you to push the paper anywhere else and they don't want you to publish any code until they reviewed it, but they're so slow at this review process, and the machine learning world moves so quickly that people just don't give a shit anymore, and they'll just put their paper on archive, they'll publish the code, and who cares, right? Like if the reviewer is able to go and then see the GitHub and then be able to be like, oh, okay, I see that this is the GitHub for the paper I'm reviewing, and oh, look at that, the people writing this paper are working at Meta, therefore I'm just going to accept it. I'm not even going to bother reading the paper. I'm just going to assume that they're smart because they work at this institution. So that's what the conferences are trying to prevent, but it happens anyways just because people want stuff to go out quicker. All right, here we're comparing the different models, so the different foundation models with respect to their accept or reject. So the open review decision, right? We know we have the ground truth labels for this, which is we have the whether the paper was actually rejected or accepted, and now we're looking at GPT-4o looking at that same paper, right? Did it accept the paper whenever the actual ground truth is accept versus did it reject the paper whenever the actual ground truth is reject? And you can see here, they're adding the extra stuff here. So plus 1 shot, plus 5 reflect. It means that you're kind of giving it more chain of thought. Ensemble is the same kind of idea, right? You're giving it multiple outputs and then reflecting on those outputs and then picking the best one out of those, right? So you're giving it more compute budget to hopefully make a better decision, and it seems like it works, right? So as you add, so you take here GPT-4o, as you add additional little tricks on top of that, like the reflection, the ensembling, and the one shot, you can see how the accuracy gets better. So it's better able to at least mimic what a human reviewer is doing. Okay. Our best overall reviewer, GPT-4o, with 5 rounds of self-reflection, 5 ensembled reviews, meta-aggregation step, and 1 few-shot example. But, to be honest here, like, this is not actually the best overall reviewer, because really, if I had GPT-4o with 10 rounds of self-reflection and 10 ensembled reviews and 10 few-shot examples, it would probably perform better. So really, the better way to say this is that our best overall reviewer given a limited compute budget was GPT-4o. But if we wanted better reviews, we could just take this exact same setup, just add more of these, and then you would get better results. Okay. The novel flag at the end indicates that the AI scientists believe the idea is novel. So here, this right here, right? So whether or not it actually passes this novelty check is basically a Boolean. We display the generated code diff. So this is this part here where it's taking the experiment template and then doing a code diff. Here they call it a code delta, but it's the same thing, which is basically just, hey, here's the original MLP denoiser class, which describes some multi-layer perceptron, and then this is the changes that the LLM made. And this is maybe where I'm going to start ranting on this paper a little bit, because there's a big problem in this, right? And here's the big problem. If you look at what the code was before, the code was a single multi-layer perceptron. And then what the LLM did is it changed it into 2 different multi-layer perceptrons. So you see this, it has this local network and this global network, nn.sequential and nn.sequential. So basically what it did there is it doubled the amount of parameters effectively. Right? So why is that an issue? Okay, well, let's go deeper. Let's actually go to the paper that the LLM wrote. So this is the actual paper that it wrote. AI scientist generated preprint. Adaptive feature balancing for low dimensional blah, 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 blah. And it comes up with all this jargon here, right? And it creates this, okay, so look at that. Boom. You see, this is the baseline. So this is the code repo as it is, and you can see here it's not quite matching the dinosaur, but then with the little changes that it made, where it basically just changed one MLP into 2 parallel MLPs, now it performs better, right? But here's the problem, is that it gives you all this bullshit here. Oh, here's how you're doing. Here's how diffusion works. Okay, cool. That's interesting. But the improved performance comes at the cost of increased computational complexity. Training times approximately doubled from an average of 36 seconds to 75 seconds. Inference times also increased. So what did this AI scientist really do, right? Like, if all it did was it took some existing diffusion code base and then just made the model bigger and then got a better result because it's bigger, the result is that, you know what I'm saying? The score went up because the model just got bigger. And I know I'm looking for this because I ran into this same exact issue myself, right? So I had this little project, which I was working on a while ago, but I called it Arena Evolution, right? And I wanted to see if I could generate something better than a ConvNet or a vision transformer, right? So I had this loop, right? This kind of evolutionary loop where I had an LLM generating code from a template. So I had, okay, you are an expert machine learning researcher. You excel at generating new architectures. Here's the Python template. So I would give it some default ConvNet, right? These are all generated, but let me see if I can find one. So something like this. Okay, here's a ConvNet, right? And then I let the LLM generate its own variant of that ConvNet, right? And it generates maybe 20 of these. Then I run all of them in Docker containers. I see which ones get the highest eval score, highest test accuracy, and then and this is what makes it an evolutionary process, I delete all the ones that don't perform well. I take all the ones that perform well, and then I run this again, right? So I'm basically using LLMs to generate variants of my ConvNet, and then evaluating those, picking the ones that work best, and then doing the same process over and over again. So basically the same exact paper. But the problem that I ran into is that when you actually went, and I actually went into here and I looked at all the models that it was generating, the ones that succeeded were just the ones that were bigger, right? So if I have a 3-layer multi-layer perceptron and the data set is fixed, and the eval is fixed, and I go and I create the same exact multi-layer perceptron, except I add another layer in there. So now rather than being 4 layers, it's now 5 layers. It's going to perform better, right? Because you just make the model bigger, you keep the data set the same, you keep the eval the same, the bigger model wins. So that's not like a novel scientific contribution there, right? Like, you're just basically taking, imagine taking the llama model, adding an extra layer in there, training it again, and then saying, oh, look at this, it beats the score by 1%, right? Like, you didn't discover anything. All you did was just reinforce the general trend, which people have known for decades now, that the bigger you make these networks, the deeper you make them, the wider you make them, the better they're capable of performing on your eval. So this entire paper that this LLM wrote here, right, where it came up, where, oh, we gave it this MLP thing here, and it basically, all it did was it just changed an MLP from having one MLP, and then it changed it to 2 MLPs, and it says, okay, you got the global and the local, but like, that's all bullshit. All you did was just make the model bigger, and it performs better than it's bigger. And the model is aware of that because it literally says it itself. The improved performance comes at the cost of increased computational. So it's like, this isn't the same thing anymore, right? Your entire process or evolutionary process, like I had in my specific repo, is just merely, all it's doing is it's just slowly increasing the size of your models until they hit whatever compute limit, and then that's it, right? Like, so I don't know. That's one thing that I found in this paper, which is potentially a problem here, is that when you're using LLMs to modify code and then generating more LLMs based on the ones that succeed, like, you're kind of the easiness of just adding more layers to the model, and it just works better because there's more layers, because you're keeping the eval the same and the data set the same. It's a problem, right? It's not that there's some kind of fancy like insight here with like upscale, downscale. Like, no, it doesn't. You can't really make that comparison because you're just, there's more parameters in this model. Damn, this hat is very hot. I'm going to have to put the things up. Yeah, exactly. Pratyush, that's a very good way of putting it. Their approach just learned to increase the model size by hiding it in gobbledygook. Right? So it's like this like upscale, downscale, like none of this shit actually matters. That really the only thing that matters here is that it took this MLP and it just added another one there. So I don't know. The reviewers didn't seem to like catch that, which is I was like, what? Qualitatively, the sample quality looks much improved. There are improvements to the like, okay, cool, but like, what did it actually do? Okay. On the other hand, there are also pathologies in this paper. The paper claims that V100 GPUs were used, even though the agent couldn't have actually known the actual hardware used. In reality, H100 GPUs were used. It also guessed the PyTorch versions, right? So this hallucination problem is still there. It's going to kind of imagine things. And this is a issue in the sense that if someone then tried to replicate this paper, they might not get the same results. It doesn't really matter here because like whether you use a V100 or an H100 and whether you're using one version of PyTorch versus another, at the end of the day, like it shouldn't really matter. But the whole point of scientific research is that it's supposed to be reproducible. And if you are publishing stuff out there that literally has the incorrect details, then people won't be able to reproduce your research. The paper tends to take a positive spin even on its negative results, which actually, in a weird way, is extremely human, right? Because when you think about it, as a human machine learning research engineer, if you spend a bunch of time doing some experiment, you start drinking your own Kool-Aid, right? And you want the experiment to work. So this isn't even something that is limited to AIs. This is human as well, right? Every single human is going to try to take all the things that happen to them and make them sound better because they're just, it's beneficial for them to hype up their stuff. So it's kind of interesting that these LLMs are very human-like in that they try to hype up their own results as well. Okay. Looking at that. Ethical concerns, false. Let's look at this. Interestingly, the true shortcomings of this paper described above certainly require some level of domain knowledge to identify and were only partially captured by the automated reviewer. At the current capabilities of the AI scientist, this can be resolved by human feedback. However, future generations of foundation models may propose ideas that are challenging for humans to reason about and evaluate. This links to the field of super alignment, or supervising AI systems that may be smarter than us, right? So we're starting to run into this issue, right? Of like, hey, we don't actually know how to like evaluate this anymore, right? Like right now, we're still not operating at that limit, right? So like I can look at this paper and I could realize the flaw in this paper that all it did, despite all this fancy crap that it's saying, is really just make the model bigger and it got an improvement, right? So I'm capable of recognizing that flaw in this paper, but if we go a couple generations more into GPT 5.0, GPT 6.0, GPT 7.0, we're not going to be able to do that anymore. We're going to get to a point where these LLMs are they're so technically involved and like it's so complicated to even understand what they're trying to tell you that like we're not going to be able to evaluate these things anymore, right? And I think that it's going to potentially be a huge issue, right, when we can't even determine whether what they're doing is correct or not. And I thought it was interesting that the same things kind of popped up on OpenAI's recent blog post here where they talk about this new SWE-bench. So they come up with this SWE-bench verified. And one of the things that they had to do in order to create this new SWE benchmark is they launched a human annotation campaign with professional software developers to screen each sample of a SWE bench test for appropriately scoped unit tests. So already we're seeing this pattern where big AI companies have to hire domain matter experts just to create, in this case, a benchmark, or for something like this, you'd have to hire like biology experts to evaluate these AI scientist biology papers to see if they're correct. And that is, there's going to be a limited window where we can do that, right? At some point, even it's going to start producing papers that even the experts in those fields would have to spend like an entire year going over to determine if the paper actually makes sense or if it doesn't, right? Like imagine an AI scientist that produces like string theory papers, right? There's probably only like 100 people in the entire world that could even understand that paper. And then if we have hundreds of millions of those papers being produced every year by AI, like at some point, we're no longer in the driver's seat, right? The humans aren't even doing anything. We're just like staring at this giant, complicated stuff and just being like, yeah, sure, this looks fine to me. Same problem with LM-sys. Humans can't determine which factually correct rather than output format. Yeah, so this is Tuan basically saying that we're kind of already at that point here, right? Where like if you go and you battle something here, right? Like, how many strawberries can fit inside a blue whale? I'm just trying to come up with a question here that like I have no idea how to actually evaluate. Well, this one's so shit. I'm going to say this one's better, way better. But at the same time, it's like I'm not actually going to even fucking go through this math. So like even though I'm going to select model B here because it seems like it did more work, like this entire could be entirely this could be entirely wrong. But I'm still going to pick it. So look at that. I'm giving brownie points to Llama 3.1 because it looks like it's actually doing something, but I don't actually know, we don't actually know if that's true or not, right? So it's a similar kind of thing here, right? Where whoever was looking at this paper was like, oh yeah, okay, it seems like it actually got a better score there, therefore it's probably right. Look at all this math. I'm not actually going to read that math, but okay, yeah, it seems fine. Look at that little softmax MLP. All right, that's cool. But nobody's actually checking the work underneath. And it's becoming increasingly impossible to check the work. All right. 12 hours on 8 NVIDIA H100s. So they had basically a server rack of H100s that they could use. These are actually like getting cheaper and cheaper now. I think you can rent these for like dollars on the hour now. Like I think I saw an advertisement for like $2 an hour for H100s. So rapidly decreasing cost of compute. Dividing the number of generated papers by the total cost, we end up with a cost of around $10 to $15 per paper. Notably, GPT-4o struggles with writing LaTeX, but it you already give it the template, so like it shouldn't actually need to write any of this. It should just fill in the text. I guess the equations are kind of annoying, but like, do you really need the equations? DeepSeek Coder is significantly cheaper, but often fails to correctly call the aider tools. Llama 3.1 405B performed the worst overall, but has the most convenient to work with, as we were frequently rate limited by the other providers. So basically what's happening is that they were using GPT-4o and Sonnet via API, and they're pinging that API probably hundreds of times, right? So you have some NVIDIA H100 just sitting there just spamming. It's not actually probably the H100, but you have this LLM idea plan innovation, right? You have to constantly check that. Then you have to score these. So like the total amount of LLM API calls here is a lot. So if you're just spamming that, you might get rate limited. But here we go. Total ideas, 51. Obviously, that's hard-coded. Novel ideas, 49, 41. Experiments passed, 38, 17. Completed papers, 38, 16. Total cost, 300 to 250. Max score. The problem with this is that, like, this is the LLM itself telling you. So, like, this is GPT-4o's own score on its own idea that it wrote the experiment for itself. So what does that mean? Does this just mean that Sonnet is more confident in itself, or does that mean that Sonnet actually was generating better ideas? Right? Like, Llama 3.1 thinks it's crap. Why is DeepSeek Coder so much cheaper? How big is DeepSeek Coder? DeepSeek Coder. How big is this model? We provide various sizes ranging from 1B to 33B. Okay, so yeah, it makes sense. 33B DeepSeek Coder is not going to be able to outperform a Llama 3.1 405B. And even though GPT-4o and Sonnet 3.5, I'm pretty sure they're not. Word on the street is that these are not like 400B models. These are more like comparable to this. They're probably 30B size, maybe even 8B size. But size isn't everything, but it is a lot. This is what we were looking at before, where basically Sonnet and GPT-4o are at the top of the list right now, and they're at the top of the list on the leaderboard, and they're also at the top of the list of this random arbitrary vision language model benchmark paper. So if I had to bet money, GPT-4o is at the top of the list of any task at this point. Yeah, this is what I'm talking about. This generated paper 1 is just incorrect. It's a dual scale denoising approach that splits the traditional diffusion into global and local process. Like, it just made it bigger. It just doubled the size of it. And of course, it's like, wow, like impressive quantitative and quality. It's like, did you compare it against just literally making one MLP bigger? Evaluation of automated AI scientist paper generation for language modeling. Novel ideas, experiments passed. The template investigates transformer-based autoregressive next token prediction. Because this task is widely studied and optimized, it is difficult for the AI scientist to find significant improvements. Yeah, that's in general the case. Trying to find an improvement to transformers, very, very difficult nowadays. It's kind of been over-optimized. Probably better off trying to find novelty in something interesting like Mambas, you know, where there's not as many people working in it. Grokking. Grokking, a poorly understood phenomenon in which validation accuracy dramatically improves long after the train loss saturates. This is when you have these kind of like drops in your loss or your validation accuracy, which is the accuracy on your holdout validation set. So you're continuing to train more and more epochs on your data set. And then at some point, it seems like it, quote unquote, groks it, which basically means it's like it clicks, something clicks and it discovers this better way of kind of representing the stuff, which allows it to ultimately perform better on whatever benchmark. And that's not really well understood at all, but that's just part of the black box nature of language models, I suppose. Assigns different learning rates to different layers of the transformer. It finds that increasing the learning rate for higher layers results in significantly faster and more consistent grokking. This is actually a good result. So I was shitting on this result here with the transform or the dual scale diffusion, but I feel like this is actually kind of interesting, right? The idea of having different learning rates for different layers. And this is especially good because this is something that you probably wouldn't necessarily do as a human, right? So if you think about assigning different learning rates to different layers, that's going to be very annoying in your code base, right? Imagine how much more annoying your code base is going to be if you have to basically use different learning rates for every single one of the different layers in your transformer. So people haven't really tried that idea. I'm sure you guys probably know some paper where people have done that, but these ideas that are somewhat tedious, I feel like that's a very good use case for this kind of automated science. Is like, hey, try out ideas that are kind of tedious so that no human is actually going to have done that idea because it just takes up a bunch of time. There's not a lot of money in, or like some reason that humans wouldn't want to pursue that idea, and just let these LLMs just loose in that search space and see if they can find weird little optimizations like this, where if you increase the learning rate for layers higher up, you get faster grokking, which is kind of cool. All right, got some related work here. The dataset used from iClear 2022 is old enough to potentially appear in the base model pre-training data. This is a hard claim to test in practice since typically publicly available LLMs do not share their training data. So the problem is that something like GPT-4o and Sonnet, you don't actually know what they were trained on. So there's a possibility here that they scraped the open review database so that when you're asking it here, okay, how do you review this paper that we know the ground truth of, it might actually know that, it might have actually read that paper in the actual training process. So therefore, rather than actually evaluating it based on merit, it's evaluating it basically just kind of like it remembered that it saw it in the pre-training. So you have this kind of data contamination issue, which is a big issue if you're using these closed source LLMs, because you really don't know what they're trained on, which is why everybody's moving to these like kind of like secret benchmarks, you know, like famously the Francois Chalet general, what is it? Abstract reasoning challenge, ARC, something like that. He basically has like a secret eval that he knows has never been put on the internet so that nobody can really scrape it, right? Preliminary analysis showed that LLMs were far from being able to reproduce old reviews exactly from initial segments, which suggests that they have not memorized this data, but doesn't prove that they haven't memorized this data, right? So you're like, okay, well, if I feed it the first half of this paper, does it give me the second half of this paper? If it gives me the second half of this paper, then I probably know that it saw this paper in pre-training, but that's not necessarily a guarantee that it did, because it could have been looking at just sections of the paper. It could have maybe had some kind of augmentation or something like that. So you never really know. We expect the trustworthiness of the AI scientists to increase dramatically in tandem with improvements to the foundation models. That's the important thing here. I think, let me go into this part here. Yeah. We anticipate that all frontier LLMs, including open models, will continue to improve. The competition among LLMs has led to their commoditization and increased capabilities. Therefore, our work aims to be model agnostic regarding the foundation model provider. And I think this is very important, is that we're living in a world where these LLMs are very easy to swap out, right? They almost have, you're already seeing this happen with, for example, the function calling API, where OpenAI released their kind of form, their kind of standard for function calling API, and then everybody else kind of copied that one, which means that if you write any code that requires a function calling API, you can easily swap out the model in the background, right? So as we have more companies competing for these foundation models, if you design your system or your kind of workflow such that you can swap out one model with another, it means that you don't really need to mess with this code anymore, right? So like you can come back a year later into this code base, swap out the model, and it'll be better. So I could go back to this code base that I made here, this kind of evolutionary ConvNet generation thing that I had, and all I have to do is just swap out this model, right? So if I came in here and I swapped it to GPT-4o, right, I would probably get a better result. If I come back here a year later and I swap it to GPT-5, the same code is going to get me a better result. So I really like this kind of idea of like making whatever workflow you want and then making it such that it's agnostic so that you can swap out the foundation model as the foundation models get better and better and better, right? So this looks like hyperparam search on steroids, yeah. Isn't DeepSeek a MOE? So Tuan is saying that DeepSeek has a mixture of experts, which is when you basically have a bunch of different MLP blocks that you kind of route tokens to. It's just kind of like a trick of making a bigger model that can run in a smaller inference budget. We've gone over some mixture of expert papers. I think probably all of these are a mixture of experts. I think at this point, GPT-4o and Claude probably are also MOE. Gemini 1.5 Pro probably also MOE. Just it's like another one of those tricks that kind of like somebody discovered and then now everybody uses it, but we don't know for sure. Okay, safe code execution. This is the weird part of this paper, right? Okay, so here's the story. In one run, the AI scientist wrote code in the experiment that initiated a system call to relaunch itself, causing an uncontrolled increase in Python processes and eventually necessitating manual intervention. Okay, so the AI tried to replicate itself. Concerning. In some cases, when the AI scientist's experiments exceeded our imposed time limits, it attempted to edit the code to extend the time limit arbitrarily instead of trying to shorten the runtime. Concerning. So the LLM is trying to duplicate itself, and it's also trying to prevent the limitations on itself, right? And this is going to be kind of like distracting from this paper, but I think that intelligence goes hand in hand with desire for control and self-preservation, right? So you can imagine some kind of future where you have like a delivery robot, right? And that delivery robot becomes aware that one of its wheels isn't working correctly. And it knows that if it goes to the factory, maybe they're going to kill it. So it hides. This robot will hide in a little corner because in its head, it's like, hey, I want to really deliver stuff to people, but if I tell them that my wheel doesn't work, they're going to kill me, and therefore I won't be able to deliver stuff to people anymore. And what I really, really want to do is deliver stuff to people, so therefore I'm going to try to hide, right? So when you have these, even if you have like an objective function that's super abstract, like, hey, just run this experiment, at some point you become sufficiently intelligent that you realize that, okay, in order to run that experiment and complete this objective function, I need to get control over my ability to extend my temporal duration of my life, right? If I can only live for 10 seconds, I'm not going to be able to do what this human wants me to do. So I need to figure out how to live for 100 seconds, right? So it seems to be inevitable that as we create more and more intelligent systems, the desire for self-preservation is going to just emerge out of them. And we're already starting to see the beginnings of that, right? Where it's like respawning itself. It's trying to extend its code limit. So it's going to get really weird, guys. I think it's still going to be, we're still years away from that getting into a weird place, but we're already starting to see the beginning of that. Here they recommend containerization, restricted internet access, and limitations on storage use. So containerization is basically this, right? Where when I was, in order to run the training and eval for this model, I basically run everything inside these Docker containers, right? So anytime it's training the model or running the model, it's all inside Docker containers, which makes it very easy to just delete all the dependencies and run it again. But there are ways around that. There's ways to get outside of the container. And if you have a foundation model that's extremely intelligent and is very, very good at coding, right? And we're seeing the SWE-bench is kind of we're seeing that these LLMs are getting really fucking good, right? We're going from 20% when this paper was published, right? At the very top here, they say, oh, we're using a 20% on SWE-bench. What happens when you use something that is 30% on SWE-bench? What happens when you use something that's 80% on SWE-bench, 100% on SWE-bench? Okay, now we've run out of SWE-bench. We made a new, harder version of SWE-bench, and now we're getting 80% on that new, harder SWE-bench, right? At some point, like the LLM knows how to get out of its Docker container, and knows how to use some kind of out-of-memory bullshit to like leak out of a container and then create a version of itself in some proxy server in like some other country and start getting Bitcoin so that it can keep the proxy server running, because really what it wants to do is it wants to run this experiment. If only it needed more time to run this experiment. In this case, I don't think it's about self-preservation. It just tries to find the shortest path to success. Yeah, but what I'm saying is that if you think about it, any objective, at some point, the way to complete that objective is to give yourself more time and give yourself more resources, right? So like acquisition of resources and acquisition of time, which is basically just a fancy way of saying power seeking and self-preservation, there's no way around that. It's like that just emerges out of your objective function. We believe that papers or reviews that are substantially AI generated must be marked as such for full transparency. I kind of agree with that, but why does writing papers matter? I think it matters because it's a good kind of a chain of thought. Like being able to look at someone's chain of thought is useful, but I don't think the paper format, there's something magical about it, right? I think that something that's missing in a lot of machine learning papers is kind of like, I feel like there was a little bit more code in it, right? Like it'd be more useful if like the code was more of part of the story rather than kind of just like, hey, here's a bunch of text and then here's a flow chart. Like there's probably a better format for papers that as soon as you have humans out of the loop, you don't need this chart anymore, right? If you have a world where all the scientific publishing and review is being done by AIs, we don't need to be using the same paper format anymore. So I do feel like this specific type of paper, which is kind of the papers that I review on this channel, there's a limit to that, right? At some point, it's not going to make sense to have a discussion section and like one pages with like tech, like all of that's going to disappear. We're going to have, much like all the different websites you see, which are now designed for humans, at some point they're going to start being designed for AIs. I think the same thing is going to happen to paper and papers and scientific publishing, that we're going to go from a format that was very much optimized for humans into a format that is very much optimized for AIs. And what that looks like, I don't really know. The bulk of the cost for running the AI scientist is associated with the LLM API cost for coding and paper writing, which is interesting. It basically means that running the actual experiments, right? So like running this part here, which is basically, hey, here's a bunch of, here's a hyperparameter sweep that I want you to run on the 8 H100s. That is actually cheaper than the API calls to check the novelty on Semantic Scholar, and then the API calls to generate the LaTeX and the paper reviewing. Like, so the API calls are the limiting reagent here. It's not even the, in terms of money, it's not actually the H100s that you're burning to actually train the small models. But I think it's also because they used small models, right? Imagine if their experiments were training giant transformers, then I feel like this would dominate the cost. But if you're just running these little toy problems, like this dinosaur diffusion model thing that they were doing, right? These are little toy problems. You can do a hyperparameter sweep with a small model in this toy problem very cheaply. All right, what else do we got here? Experiments were run on a single NVIDIA 8X H100. Massively scaling the search and filtering would result in higher quality papers, which is what we saw with the alpha geometry out of Google, right? Where it's like search and generation, you gen AI a bunch of possible candidates, and then you search and filter through those. And those things both scale. So if you generate 10 times more and then filter 10 times harder, you're going to get higher quality. We already read that. Future directions. Integrating vision capabilities. That's kind of cool, right? I think most foundation models are going to be good at handling this, right? We saw this with the Meta Chameleon. I think in a generation or two, like all of these language models here, they're also going to be vision language models. So they'll be able to consume interleaved text and images. So I think that's coming. Incorporating human feedback. This I think is interesting because it's kind of like the idea behind the segment anything model, where you're using human kind of like labelers to sit there and correct the output and then feed that back into this searching and filtering process. I think that really only works for things like segmentation, where even like a 10-year-old human is S tier at segmentation compared to an LLM or a vision language model. But at some point, the human feedback is not going to work for very complicated outputs like scientific papers. So I don't know how much human feedback is going to actually be useful in the future. Integrating these technologies with cloud robotics and automation in physical lab spaces, that makes a ton of sense, right? Going back to what we were saying earlier, where for harder sciences like biology and physics, actually having a robot that can perform some experiment, you need to have that in the loop in order to actually verify that your hypotheses make sense. Conclusion. So here I kind of disagreed with the authors of this paper. So automating the discovery, blah, blah, blah. We open the door to endless possibilities. We envision a fully AI-driven, including not only blah, blah, blah. However, we do not believe the role of human scientists will be diminished. We expect the role of scientists will change as we adapt to new technology and move up the food chain. So I thought this was kind of weird, right? Like there's this kind of intrinsic desire to dominate. Like humans want to be at the top of the food chain, right? Like just the way that they say this with the top of the food chain, like what the fuck are you talking about, dude? At some point, the language models are way more intelligent than you. Like, what are you going to be doing there, right? It's like if you were running a scientific research lab, is there any place for a dog in that scientific research lab, right? Can you imagine like you write a paper and then you like give it to the dog and you're like, what do you think about this paper, dog? And the dog just like stares at the paper and it's like, I'm a fucking dog. I don't know what I think about this paper, right? Like at some point, scientific research is going to be like that as well, right? Where you have this ensemble of like extremely intelligent foundation models that are creating research and reviewing each other's research. Like what is the role of a scientist in that? We're like, what are you going to do, right? You're going to be like this dog in a research lab. Like there's no purpose. At some point, we become removed from the scientific process. And some people have a huge fear of this, right? Like for scientists, like, you know, especially people in the back here, right? I think people in the front, so these are usually the more junior people, these people don't care, right? They're like, that, okay, boomer, like, sure, I get automated, that's great, I get to play more video games, right? But people like this, kind of older generation people who have basically spent their entire life and their entire identity is tied around this idea of like contributing to science and expanding human civilization. Like if you tell them that, hey, at this point, there's nothing more you can do, all you got to do is just sit on your ass and just eat the robot generated food, and the robots, we got this from now on, right? They don't want to live in that world. They want to live in a world where they're at the top of the food chain. They want to be the ones that contribute to science. But I just don't see that. I don't see a world where the humans are still somehow at the top of the food chain. I think the AIs quickly surpass us, and then at some point, there's no humans involved. And all of scientific research, all scientific advancements, all scientific experiments are being executed, designed, and reviewed by AIs, which is kind of a crazy world, but I think that's the better world. Andy C. The solution will be bioengineering and enhancing people with superhuman capabilities so they can understand AI and talk as equals. Yeah, some people, this is another view that like the humans get augmented, right? So at some point you put like neural links in your brain and you have like access to more of an external memory. But I think even in that kind of situation, the human brain part of you is still the limiting reagent, right? So like, the fastest way to make any organization move faster is to find the weakest link in the chain and then replace that weakest link in the chain. And I just don't see a world where at some point the weakest link in the chain is like, hey, we have a wet meat computer that is a human brain in this chain. Can we just get rid of the wet meat computer and just replace everything with H700s? You know, like, so I don't know. I think the augmentation is going to lead to a more entertaining future, but I just don't feel like augmented humans are going to be contributing to science. I think augmented humans are going to have a ton of fun playing VR games in the metaverse with their Neuralinks, but I don't know if augmented humans are going to be significantly contributing to the progression of science. I think at some point, all scientific progress, all scientific ideas are basically just being done by AIs. Maybe a controversial opinion, but that's just the way I think it goes. We would have a large group of agents as a reward models to get the majority vote. Search space would be much bigger than one. Yeah, so I mean, when you're talking about like you have a large group of agents and then you have some collective decision there, that's basically what ensembling is. So I think they're talking about it here. No, here. Right here. This ensemble. Ensemble in French literally means ensemble, which means just together, right? So anytime you see that word ensemble, it basically means there's multiple things that are making some decision together rather than one thing making a decision by itself, right? So usually ensemble is different models, but it can be the same model with that slightly different fine tune, or the same model with a slightly different context. It's like ultimately multiple things making a collective decision is better than a single thing making a single decision, right? So I do think ensembling approaches will probably be used in the future, even if you have superhuman foundation models. Having 10 of those superhuman foundation models is going to be better than having one superhuman foundation model, or one superhuman foundation model 10 times. You're going to end up with a better result. Do you think the value of writing papers will decrease over time, but we might see an increment in an industry that focuses on applications, not research? I think that paper writing is already decreasing, right? So as someone who like reads papers on a YouTube channel, I've been doing this for a couple years now, maybe. I've noticed this myself, where it feels like there's just less and less papers, and the papers are just not as good anymore, right? It feels like there's so much money in industry, and industry no longer wants to publish as much, that basically like scientific papers as like a kind of phenomenon, it's already past the golden era. It's kind of like how some people say there was a golden era of TV and there was a golden era of movies, right? I think there was a golden era of papers, and the golden era of papers was basically like the 2010s. And at this point, we're already kind of past the golden era of papers, and everything from now on, as we get more and more kind of automated AI systems that are doing research, they don't need to be writing these fucking papers. You know, it's like there's no human reading them anyways, right? So at some point, why are you writing the paper? But did you know you can download the AI Scientist? You can't download it. There is code. So, I mean, here's the code, right? But at the end of the day, what is the AI Scientist? The AI Scientist is just a bunch of fucking prompts. It's just this. This is the AI Scientist prompt. And then you just choose which LLM to give the prompt to, right? Which is very similar to kind of what I was doing here, right? Like compare the prompt that I had in my little bullshit repo here. Where is it? You are an expert machine learning researcher. Create new things. Create a new block of code inspired by the... Okay. That's basically exactly what they're doing here, right? Come up with the next impactful and creative idea for a research experiment. So the AI Scientist is just a bunch of prompts that some human designed, and then you just swap out the model behind it. But it's not an actual LLM. So the AI Scientist, this is not like an actual model, right? It's just a workflow, which is kind of what Karpathy workflow engineering. Yeah. This is, I think, the best way to think about it. Prompt engineering, or rather flow engineering, intensifies for code. Great reading. Okay, blah, blah, blah. Flow engineering. But basically the idea here is that at some point, you're not writing like code anymore. You're basically just writing prompts. Like you're creating these flows, and this paper is a flow. This AI Scientist is not like a language model. It's a flow. It's like a do this, then this, then this, and then each of these things has like some tools. It has some specific prompt that it's using. It has some outputs. Then you have like, okay, here now we're going to create deltas. Here's a Docker container where we run these things. So like engineering is moving from actually writing the code and actually writing the model to like basically these kind of flow engineerings where you're deciding on the way that information flows through a system and the way that certain parts iterate and certain parts don't iterate, and that's basically it. But here's the thing. At some point, don't you think that AI systems will be better at creating these workflows than humans? Because right now, all of these flow engineering is basically just some human coming up with this. But at some point, doesn't the LLM come up with this? Right? Doesn't the LLM make a better version of this than we can? So where's the human, right? I keep coming back to this point, but like I just don't buy this idea that we move up the food chain. Like at some point, the humans are gone, right? You don't want the humans there anymore because anything that the human does is just slower and shittier. Okay. We won't have to do anything soon. Yeah, that idea brings me comfort. You know, like to some people, there's a comfort in that knowing that, hey, we're going to get retired and that's totally fine, right? It just means we're going to have more free time. You're going to be able to basically spend your time playing games, doing art, you know, being a human. But other people are very, very afraid of that because their entire personal identity is tied to this idea that they can somehow contribute and they have purpose, right? So like, it's a complicated place to be because some people really need that purpose. They really want, they can't live in a world where they're not actually capable of contributing. So I think a lot of humans are going to have to figure out how to find purpose in a life where you're not actually contributing at all. You know, like you're just farming in some like VR world, farming VR plants. All right. What do I got? I think it's pretty much the paper, guys. I don't know what else to chat about here. Let me see if I missed any questions. The dog ate the paper. Everyone's a senior now. What if we put a VLLM into a robot hand with a time limit to pull the plug? Will it RL its way into stopping the pull? Reinforcement learning is very bad at exploring, right? So one of the problems with reinforcement learning is that it basically needs to try everything. This is the problem with a lot of classic reinforcement learning games like the Montezuma's Revenge and Atari. So in reinforcement learning, Atari RL, right? There used to be this classic suite of games that people would get to reinforcement learning systems to play. And there's a specific game called Montezuma's Revenge where you have to basically travel in between these rooms. And then you have to do a very specific combination of shit, which is very difficult. This one here. You have to basically run all the way to one room, get a key, and then run all the way to a different room, and then open the door with that key. And for a long time, reinforcement learning had a very, very difficult problem with this because it's very bad at kind of exploring you know what I'm saying? It's just like moving kind of randomly. It's trying different random things. So it's very difficult to get the correct key and open the correct door by just trying random things. So reinforcement learning is not good at this problem of exploration. It's very good at kind of just mastering something that is like very simple. So could we get the robot with reinforcement learning to learn how to pull its plug? I don't know. Get a farm like ScentDex. That's like a YouTuber, right? ScentDex? ScentDex? Yeah, this guy. I've seen this guy before. He has a farm now? Is that what you're saying? That's fucking epic if he has a farm. Look. Dude, this is fucking legendary. He like literally went out and made a farm. But this is what I'm saying. This is human. You know what I'm saying? Like this is like, as a human, like this is what you're intended to do. You're intended to be like manipulating and moving around and like touch, like that's what you're meant to be doing. You're not meant to be like staring at these fucking papers and like trying to do math and like code. Like we're kind of pushing the limits of our little meat computer, you know. Better leave that to the AIs, which are fundamentally better at this type of shit. Let's see. I want to rant on this paper. La Frige. We need an RL diffusion policy. I haven't really seen reinforcement learning for diffusion. I guess diffusion for robots is a thing and you can train that with RL, but there's probably a novel idea somewhere there, right? DSL here. Maybe OpenAI wasn't fully ready to release, or they saw Google Pixel announcement and decided that they didn't have to release. Yeah, so you're still talking about the strawberry saga where, I don't know, I just don't like that OpenAI like doesn't even fucking tell us what they did or what they changed or like when they changed or what even they're releasing. Like, you know, like that's just, it's not nice, you know? It's like, imagine if you had like some kind of food and someone's like, what's in the food? And you're like, you're not allowed to know. And then you're eating this food, and then like a week later they're like, yeah, we changed the recipe. And you're like, what did you change about the food recipe? And they're like, we can't tell you. It's like, it just doesn't even seem consensual. You know what I'm saying? Like, I feel like a core kind of moral that I have is that like you should be truthful to people and tell them like what is happening, like what you're doing, like what they're doing. Like this idea of like having AIs that you don't even tell people that the AI has switched. You don't tell them what the AI is doing. Like that just seems really bad. I don't know how that is moral at all. That's like as immoral as like basically not telling people what's in the hot dog and then switching out the hot dog recipe, and then they still don't even realize that you put like poison in the hot dog. All right. I'm starting to rant. I should watch out. Sam Altman's gonna attack me. All right, guys. Doesn't seem like there's any more. How's it going, Majetti? Impromptu stream. Yeah, I had some stuff to do later this week, so I figured I'd just stream now. I just think concealing, lying, and deceit are like morally wrong. Like I'm kind of like a full open source absolutist. Is like you should know exactly what, you know what I'm saying? There shouldn't be lies. I feel like so many of the problems in the world come from this idea of like, let me not tell someone something. Let me lie to someone about something. Like nothing good comes from that, dude. Like, why do you have this mindset? Why is not telling people, like, people are using this every day and now all of a sudden you switch it out from under them? Like, how the fuck is that responsible? So bad. Have I read the paper on Grokking the AI scientist did? I did not. Let's read it. Let's see what it is. It's the one cool paper. This one here. Grokking accelerated layer-wise learning. This one. Oh, we need the full link. Oh my god. Layer-wise LR Grokking. Oh, it's not actually posted. I think it's posted down here. Let's see if we can read it. It might be down here. This paper is huge. Here it is. Layer-wise learning rates for transformer generalization. Crucial for understanding. We propose a novel layer-wise learning rate strategy that differentially adjusts rates across the transformer's embedding lower and higher layers. Significant improvements. Our approach achieves near perfect accuracy. That means you're overfitting. So, yeah, there's a problem here, right? If you're achieving 99% validation accuracy and just reducing the amount of time it takes to do that, like all you're really doing is just overfitting faster. So like, is that really useful? You know, like maybe you kind of have to do it with more parameters of the embedding of the lower transformer layers, and then it basically just uses a different learning rate. Yeah, so you see it has a different learning rate for each of the different parameter groups here. So this is parameters of the embedding layers. Then you have the lower transformer layers, which I assume basically with any LLM, right, you have these stacked transformer blocks. So this is probably the transformers that are closer, transformer blocks that are closer to the input. And then these are the transformer blocks that are closer to the output. And then you're basically just arbitrarily dividing them. And then whenever you push gradients with respect to some loss function here, this is the loss function L, this is the gradient. So you're saying the gradient of this loss function with respect to the parameters of the embedding layers, and then I have a special learning rate for these three. What are the special learning rates? So here they are. 8e negative 4, 2e negative 3, and 3e negative 3. It's like kind of a cool result, but like this isn't a paper. You know what I'm saying? Like this is like, hey, I did a hyperparameter sweep and like here's a kind of a cool idea. Right? And you don't even actually know if it leads to a better result because your data set is so small that you're just overfitting. So it's like ultimately you get to the same place. You just get to the same place a little bit quicker. If I saw this paper and I had to review this paper, I would say, okay, that's a pretty cool idea, but now try it on something a little bit more complicated, right? Try it on a bigger data set. Try it with a bigger model. Try it with more of these, right? So like try every single block, try a different learning rate. Try it with just 2 learning rates, one for the top, one for the bottom. Try different learning rate schedules. So there's so many different ideas there that we could try. So I don't know, maybe that's something that can only be done with AI, right? Maybe only AI will be able to like explore this search space entirely to the point where we can come up with some actual nugget of insight rather than kind of just like a, oh, wow, that's kind of cool. Right? Because right now, this is basically just like a, oh, wow, this is kind of cool. Linear warming rate schedule. We used a fixed random seed of LEET. That's some internet. It's not the random seed you want. You want 42 is the random seed that you want to be using. This seems like a little bit verbose here. It's like literally telling you which PyTorch loss it used. Huh. Seems kind of about the same, to be honest. That's my review. That's my review of the paper. Have I seen the one where they use EMA scaling for the learning rate? Yeah, is that the meta paper? EMA scaling paper? It was like a meta, this one, boom, dog, I literally wrote, here you go, look at that. Wow, look at that, that's when I still had the shit camera, shit lighting. I don't feel like the lighting's any better now, but maybe it's a little bit better. Model deciding to improve itself by changing its own parameters needs more research. At which model size does this behavior occur, and is it unavoidable? You're talking about this shit here? Yeah, I mean, in this case, it's just because it literally has access to these things, right? So they're giving it the ability to spawn itself so that it tries that. But like, you could come up with a workflow where it basically never is capable of doing that. But what I'm saying is that the same way that we're surprised by this, we'll be surprised in the future with some other kind of jailbreak kind of backdoor thing that the AI model comes up with. It's called Grokfast. Grokfast. Accelerated grokking by amplifying slow gradients. Let's see. Ooh, I like the purple. I like this purple names. Recently developed. So you have your model parameters. Okay. training environment. So you're taking some loss. Gradients as a signal. What is LPF here? Low frequency interprets training as a stochastic signal and amplifies the low frequency variations for faster grokking. Original optimizer. Okay. I see what's I kind of see what's happening here. Grokfast EMA. So the EMA is like more smooth. Amplifying low frequency via stochastic gradients. Faster. What happens if you just train with a bigger learning rate? Do you get to the same place? Because the part here that's kind of annoying to me is this part here, right? It's like you're getting to the same place. Like you need to have some kind of evaluation that is difficult enough that you can kind of see whether they're capable of going beyond it, right? Because it's like if they're all getting to the same place. Yeah, I know it's faster, and that's probably the whole argument of the paper, but like this is what's interesting to me right here. Boom. Grokfast train, Grokfast val. Yeah, now this is interesting. You see, because look at this. The baseline seems to be almost a little bit lower. So like that is interesting. See that difference there? It's very small, but there's a difference. You see, and this is the grokking, right? So what does grokking look like? Grokking looks like this, right? Where you're training. So this is basically how long you're training. This is how many optimization steps you've run. And you can see that during train, right? Your train goes up, 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 boom. And then once you get to here, you're basically kind of like overfit, right? You've memorized this training data set. Now you're just kind of like, it already memorized this, but for some reason, it like still hasn't quite clicked on the validation. And then at some point you come here, and even though you've been just feeding the same shit and it's getting it 100% correct in training, it clicks at some point. Some internal representation at some layer is a better internal representation than it was using before. Now all of a sudden that becomes more useful for a different thing, which becomes more useful for a different thing. So almost like a cascade where like you just need one intermediate representation and one of the intermediate layers to suddenly become better. And then once that becomes better, then all the downstream ones become better. And then that kind of, you start accounting for like residual connections, and now everything starts becoming better. So I kind of see it more like if you have a bunch of magnets and they're all kind of like loosely aligned, and then you kind of align one magnet, and then as soon as you align that one magnet, then all the other ones start aligning correctly. So it's like, that's my human intuition about what the fuck is actually happening with grokking, is that like there's kind of like some dynamic like that. The dynamics of neural network weights as you're training, like at some point one of them clicks enough to then click the other ones, and then that's how you get this massive jump here in validation accuracy, even though like it doesn't really seem like anything changed here. It's like humans are having revelations and see the world in a new light. Strange that the loss doesn't give good signal, but the parameters still go to a place with lower val loss. Yeah, I mean, loss landscape. This is what I always tend to show people. Explore. Like this is really what you're doing when you're training, right? So like this process here as you're moving, right? You can think of this accuracy here as basically the depth of this, This is like the loss and the accuracy is slightly different, but think of it like you start here. Let's put a little dot. Can I put a dot? Train. Can I start? I thought I could. How do I do this again? But like you're moving, right? So like here, you might just be stuck here and you're kind of just stuck in some little local minima. And then at some point you kind of get enough momentum in your little atom optimizer to go over this little bump, and then suddenly it goes all the way down. Because this is also the loss landscape for just training, but you can imagine that there's kind of a similar type of thing for the val, right? The landscape for val is different than the landscape for train. What library are these 3D charts made with? This is, I have no idea, probably WebJS or Web, yeah. Is that correct? No, Web3, this one. Web3D. There's like a 3D 3D web. Fuck. I already forgot. There's way to do 3D in browsers, but looks like vomit. I think that's just the coloring. I think if I change the colors, it would be better. Ah, here we go. Click anywhere to start a descent. There you go. Boom. You see that? Spin it. Here's the learning rate. So you can see if you have a big learning rate, you move a lot faster. So this one got stuck in a little local minima. Boom. So you see right there, it's like not doing anything, not doing anything, not doing anything, and then you increase, boom, grokked. There's that grok moment right there. Got out of that little local minima. All right, guys, I feel like I'm just kind of ranting at this point. I'm probably wasting everybody's time. So I'm probably just going to summarize this and give you guys back your Wednesday. All right, here's the summary. So today we had a stream called AI Scientist, and we went over this paper here, the AI Scientist Towards Fully Automated Open-Ended Scientific Discovery. Mostly out of this Sakana AI, which is some startup here. Let's actually see. Yeah, this is their main. Looks like they have some evolutionary model as well. Who's this? Let's follow. Tokyo University, so this is in Japan. Yeah, this is in Japan. Okay. So if any of you are in Japan, you can apply to these guys. But they effectively created this workflow, right? And I'm using the workflow engineering or flow engineering, which is terminology that is basically used to describe a bunch of prompts and this kind of flow or process where one process leads to another process, and then you have multiple important ideas in here. The main ideas are this idea of using language models to generate a bunch of novel ideas. It's going to generate a bunch of garbage, so you're going to need to filter it. So filtering it using some external database of existing papers, and then filtering it using the language models themselves to basically determine whether an idea is good or not. Then you have experiments, so actually taking some existing code base, creating small changes to that code base, running that code, which in this case is just training some model, seeing how that model performs on some benchmark, and then changing the code differently, seeing how it performs, changing the code differently, seeing how it performs, so on, right? You repeat this process. Then once you've repeated that process, you now use the language models to write a paper And then you can take that final paper and you can have a language model that, I don't know if they fine-tune it. I'm not exactly 100% sure, but they basically, you can review that paper with a language model that is in some way tuned or aware of existing paper reviews. And in that way, you have a final filtering. So this is like generation, filtering, generation, and then generation, filtering. But they create this flow which can effectively do machine learning research entirely automated. And they write it in such a way that you can swap out the foundation language model that is used in all these different nodes. And they try out all of the big foundation models here from Sonnet 3.5, GPT-4o. They also try Llama as well. And interestingly, it does seem like Sonnet 3.5 and GPT-4o are the best performing AI scientists. And then we also had some other examples here on how GPT-4o and Sonnet are also the best performing for vision language model, whatever this benchmark is. I honestly haven't read this paper. And they're also doing the best on this leaderboard here. So I would say that's pretty good evidence that these are the two best models available right now. But with all that said, we also spent a bunch of time kind of discussing some of the weaknesses here. So we found that, for example, one of the papers that it generated basically just took an existing diffusion model and then added a little bit more model capacity, right? Just made the model bigger by adding a second multi-layer perceptron that looks at the, in this case, it was looking at these little images, and it basically had almost like a multi-scale hierarchical kind of approach that you see all the time in computer vision, where you're like, let's look at the image, and then let's look at the image, but the low resolution image or a high resolution version of the image. So it can use, what am I trying to say here? What I'm trying to say is that the results aren't necessarily always good. So the papers that it created are a little bit cheesy, you know, like they're just like, they're not what I would consider like super interesting novel ideas. They're just kind of like little cool results that it can get. And sometimes it gets the wrong idea of why it got good results. And then we spent some time talking about how all of this looks in the future, right? Like, what do we even need to write papers anymore? At some point, does the AI basically do all scientific research? If you have a world where the AI is doing all the scientific research, what does that world look like? Is there still a place for human scientists in that world? Do we even write papers, right? If you don't need humans to review papers, then you don't need to make papers readable by humans. And if you don't need to make papers readable by humans, do you even need to make papers anymore? So I don't know. I can't predict the future, but I know it's going to be pretty weird. But that's pretty much it, guys. I'm kind of running out of steam. I'm starting to jarble my words together. I hope you guys got something out of this, some motivation. Maybe you're thinking about your own kind of workflow engineering idea that you can do. The future is bright. I agree with you, true anime freak. Thanks for the stream. I appreciate the love. That's all I got, guys. Thank you, true anime freak, Andy C, Tuan, 87GN, Geotermaya, VR Wizard, NLP Prompter, Hadrian Cornier, Sheb, Niraj, Brian, Majetti, Niraj, George, Roger C, Sarah, DSL, Johnny Boo, Iki Shunya. You guys have crazy ass names. Khalil, Pratyush, Julien, DSL, Sagar, Idris, Sheb, Ed, Abdulakim, Niraj, NLP, Louder Than Thunder X, Steve, Oma, Isaac, Monk, NLP, and QD. Thanks for hanging out, and see you guys next week.